You should just do it while I figure out what.
Okay. So just really quick, I'm sure you guys already got the email, but there's the elevator talks today from 4 to 5. It's just going to be about 6 grad students giving 6-minute talks about their thesis topic. So that's today. So come by if you can't make it. Well, we were thinking about that, but we have this room, so it'll be in 211. That was something.
Okay, so what I wanted to start with today is prove this theorem for you about how the Hilbert series of modules kind of propagates along a free resolution. So I already stated this. Let's see, what's a good notation here? Let's do this. So basically, if you have a free resolution of M, then the Hilbert series of the Hilbert function and the Hilbert series of M is given by the alternating sum of those of your free modules. So this is what we want to prove. And what I illustrated this last time in an example, and remember that the point is that these things are very easy to compute, the Hilbert series of free modules, and this way we will be able to compute the Hilbert series of our target module M, if we can resolve it. Okay. So here's a proof of this fact. It goes like this. Let's see. I mean, remember what it means to have a graded free resolution is that all of these maps that I call them delta r minus 1, etc., up to delta, I guess this would be delta 1, delta 0. So these guys need to be degree preserving, right? So that means that if you kind of take the pieces of degree d, then the piece of degree d here maps to the piece of degree d here, etc. And that means that you're also going to have an exact sequence if you pay attention only to degree d. So what I want to say is that in degree d, this looks like this. So we can make our maps restrict to maps in each degree. Okay. And this right here is going to be an exact sequence of what? Well, what are these things? Each one of these guys is the dth graded piece. Right? So for example, M sub d is the homogeneous elements in M of degree d. Okay? And those guys are a vector space. We talked about this. In each level we have a vector space, and that's basically the dimension that we're after, right? And this is going to be an exact sequence of vector spaces. So what I mean by this, maybe let's clean up the notation a little bit. So I'll call this VR, I'll call this V0, I'll call this V, okay? And so what do I want to say now? I want to say that if I look at a piece of the sequence that looks like this, okay. So this is delta I plus 1, and this is delta I. And so I want to say the following, that what is the image of delta I? Well, the image of delta I is something that lives inside here, okay? But by the isomorphism theorem, we know that the image is equal to this mod the kernel. They're isomorphic, right? Okay, so this is by the isomorphism theorem applied to here. The image of this map is this mod the kernel of this map. So we have that. But we have to use the fact that this is an exact sequence, right? And remember that exact means that the kernel of delta I equals the image of delta I plus 1. Okay? Sorry, so this is an isomorphism. They're not equal, but they're isomorphic. Okay? And this is equal to Vi mod the image of delta I plus 1, because the kernel of delta I is exactly equal to the image of delta I plus 1 by the exactness. Okay? So we're good so far? So what do I have here? I have two vector spaces that are isomorphic, and that means that they have the same dimension. Okay? So the dimension of the image of delta I is equal to the dimension of this thing right here. Okay? But remember, what is the dimension of a quotient? The dimension of V mod W is equal to the dimension of V minus the dimension of W. This is a fact about linear algebra. Okay? So that means that the dimension of this guy is the dimension of Vi minus the dimension of the image of delta I plus 1. Okay? So then I want to say the following. I want to take this equation and write it as the dimension of Vi equals the dimension of the image of delta I plus the dimension of the image of delta I plus 1. Now, sorry, let me not do this. My apologies. So we're going to take this equation, okay? And now we're going to apply it to I equals 0. So for I equals 0, what does this say? It says that the dimension of the image of delta 0 is equal to the dimension of V0 minus the dimension of the image of delta 1. Right? But what is the dimension of what is the image of delta 0? Well, remember that because this is an exact sequence, this delta 0 is a surjective map, which means that the image of delta 0 is this guy, which I called V and I also called MD. So this is just the dimension of V. Okay. So I'll write it like this. So this is for I equals 0. Okay. Now, why is it that I'm trying to do this? Because you see, the dimension of V is the dimension of MD, And that's exactly the Hilbert function at D. What this H sub MD means is this is exactly the dimension of MD. And so what I'm trying to do is get a formula for that guy, right? And so that's what I started with. So dimension of V is equal to dimension of V naught minus dimension of the image of delta 1. Okay? But now I have a formula that tells me what the dimension of the image of delta 1 is. So I plug that in. So what is the dimension of the image of delta 1? It's the dimension of V1 minus the dimension of the image of delta 2. Okay. So now I've expressed the dimension of V in terms of the one of V0, the one of V1, and this one. And what's this one? Well, I have a formula that tells me what that is. So this is dimension of V0 minus dimension of V1 plus the dimension of the image of delta 2 is the dimension of V2 minus the dimension of the image of delta 3. Okay. And so I guess you see the pattern here. Basically, I can keep doing this, and eventually when I do this all the way to the left of the diagram, what I am going to get is the dimension of V0 minus the dimension of V1 plus, etc. And this is exactly the summation of this. And you see this is exactly what I needed to show, because the dimension of V is the Hilbert function of M at D, and this, remember that Vi by definition is Fi sub D. Okay. The dimension of Fi sub D is the Hilbert function of Fi evaluated at D. And that's my proof. Good point. This is I, this is I, this is I, but this is I also. Thank you. Okay. Any other questions about this proof? This is a very general fact, by the way, about exact sequences, and I mean, we're doing it for modules, but basically the proof that I did is for vector spaces, and it basically says if you have an exact sequence of vector spaces, then the dimension of the last guy is the dimension of this minus this plus this minus this plus this, etc. So that proves this, and using this, you get this, because basically what this is the power series of this guy, and what this is the power series of these guys. So this follows right away from this one. Okay. All right. So that's one thing that I've mentioned a lot, and finally we get to prove it. So let me show you some applications of this. So first application is that if you have, this is just a special case. If you have an exact sequence of graded free modules, sorry, not necessarily free. It's an exact sequence of R modules, of graded R modules. And the maps are degree preserving. So, I don't know. So we should have the same condition of being graded here. So let me call that a graded exact sequence. And what that means is exactly what we've been requiring here, that this map takes elements of pure degree D to elements of pure degree D. And this guy takes elements of pure degree D to pure degree D. So if we apply this argument to this setup, what we're going to get is that the size of n is equal to the size of m minus the size of L, where size means Hilbert function or Hilbert series. Okay. So basically here we just stop at r equals, I don't know, 1. Given the same argument, then you can conclude that the Hilbert series of the middle guy is equal to the Hilbert series of the left plus the Hilbert series of the right. Okay. I guess I just switched notations. I've just been calling this H, right? So call it H. So what this says is that if you have a known module, and you can squeeze it into two known modules, so if you know the sizes of these guys, then you have the size of M. The proof is exactly the same as what I just did. So this is not an example, it's more like an observation. Let me show you another observation that is important, which is this. If I is a homogeneous ideal of R, then the Hilbert series of R mod I is just the Hilbert series of R minus the Hilbert series of I. Okay. And remember that R is, for most of our purposes, R is just a polynomial ring. And so this is just 1 over 1 minus x to the n. Or if we have a finer grading, it's finer, but we know this guy. Basically, what this tells you is that computing the Hilbert series of an ideal is the same thing as computing the Hilbert series of the quotient by the ideal. If you have one, you have the other one. Okay? So I think this is good practice. How do you prove a statement like this? You need to make an exact sequence that will prove it for you. So what do you want to... So let's just come up with a proof on the spot. Well, I already know a proof, but maybe you guys should come with a proof on the spot. This will be good practice.
What's a homogeneous ideal?
Homogeneous ideal is one where the generators are homogeneous. I mentioned this when we started talking about graded modules, that an example of a graded module was a homogeneous ideal. I said that not every ideal is a graded module, but if the ideal is homogeneous, if all the generators have the same degree, are homogeneous, each generator is homogeneous of some degree, then that means that I is a module and R mod I is also a module. So that's what we need for this equation to make sense. So proof. Okay, well, we need some exact sequence that will do this for us. So I'll take suggestions. Well, give me at least one of the elements of the exact sequence. We need R mod I, right? We need R mod I and R and I. We just need to know where to put them, right? So where should I put R mod I? At the end. So you're telling me to put it here. So so then what else? Someone else. What would you put here? R, yeah? And what would you put here? Well, can't really go wrong at this point. You don't want to put 0 yet, so you put I. And since we only have 3 terms in the equation, maybe this is where we should stop. Okay. Well, that's almost a proof. Now we just have to justify that you can actually do this, right? So the point is, if you manage to pull off an exact sequence like this, then you would have a proof of that statement. But you need to figure out what your maps are going to be. Okay? So hopefully it'll be clear what to do. So how do you map I to R? What's kind of a natural map from I to R? It's just inclusion, right? Because I is a homogeneous, I is an ideal in R, so that means that these elements I live in R. And so this is just kind of the identity map. It's just inclusion. Every element that lives here lives here. And how do you map R to R mod I? It's kind of a natural choice, which is quotient by I, right? So you take an element A, and you map it to the coset A plus I. So that's kind of the, I mean, let's really write this out. So this is F, this is G. So what is F going to do? It's going to take an element of I and it's going to take it to I. And what is G going to do? It's going to take an element of the ring and take it to this coset. Remember, you don't get to choose what this map is because everything goes to 0. You don't get to choose what this map is because you have to map 0 to 0. So what things do we need to check? First of all, we need to check that F is injective. Well, it's injective because it's the identity, right? So that means that I am exact here. Then we need to check that this map G is surjective. So does every element in R mod I get hit? Well, yeah, because every coset comes from somewhere. So this is surjective, so that means that I have exactness here. And what's the last thing that I need to check? That the image of F is the kernel of G. So what is the kernel of G? Well, the kernel of G is the things that map to the 0 quotient. To the 0 coset, I'm sorry, right? That's exactly I. I is precisely the things that get mapped to 0 here. And I is the image of F. Because F is the identity. So that's a proof. And this is when the machinery starts to pay off because you cannot get proofs for free. You just think, well, if a proof along these lines would work, then it would have to look like this. And then it's really not a lot of places that you can go wrong here. Everything is fairly natural. Whereas if I asked you to prove this 2 weeks ago, maybe you could do it, but you would have to work hard. You'd have to come up with some ideas. But your ideas probably would amount to this same proof, and now we just have the machinery to do it. All right, so that's good. So here's a theorem that is very nice. The corollary of this and this is due to Hilbert. It says that the Hilbert series, so let's say that R is the polynomial ring in n variables. And the Hilbert series of any graded R module is of the form Hilbert series it's always some polynomial divided by 1 minus x to the n. So this is a very nice result because, I mean, the way that we define this Hilbert series, we just said, here's a Hilbert function, and then make a generating function for it. And a priori, there's no reason why you should always get such nice answers. You could get, I mean, you guys know, you've taken analysis, right? So you know how bad series can be. And it's very rare that you would take a random series and it would look like a nice polynomial divided by 1 minus x to the n. But this is what Hilbert realized, that it's always true. And the corollary of this is that there is a let's see, what's the good way to say it? The Hilbert function h sub m of d agrees with a polynomial function. Function, I don't know, f of d of degree less than or equal to n plus 1, I think, n, for all large enough d. Okay. So what is this saying? This is saying that no matter what module you take, if you look at the Hilbert function, actually that Hilbert function is a polynomial, always. The only thing that might go wrong is that the polynomial has the first few values off. So maybe at 0 you get something random, at 1 you get something random, at 2 you get something random, and from 3 on you just get one polynomial, which you can kind of think of as the real growth of this function, and some anomalies might take place at the beginning. Again, this is an amazing theorem a priori because this was just some function, and there was no reason why we should expect it to be polynomial a priori.
Is that what it means when you eventually polynomial?
Yeah. What did I say? Agrees with a. Yeah. I guess I wrote that in the homework. Yeah. So you should recognize this because in the homework I'm basically asking you to prove that these two conditions are equivalent to each other. And so I'm going to prove this one, and then you will prove that that's equivalent to the other one. How do I prove this one? Actually, I have nothing to do, because you see, the Hilbert series of m is the alternating sum of things that look like 1 over 1 minus x to the n. So you couldn't get anything different. Let me say it a little bit more carefully. So proof, well, just resolve this guy. Okay. And what this means is that if I can prove that all of these guys have the right form, if each one of these guys is a polynomial divided by 1 minus x to the n, then as an immediate consequence, this guy is going to be a polynomial divided by 1 minus x to the n, because it's a sum of things of that form. So this is the kind of thing that I'm telling you that a resolution is good for, because this is a property that is very easy to establish for free modules, and it propagates along an exact sequence, and m inherits it by the exact sequence. How do I prove this? Well, what's a free module? A free module is a direct sum of free modules, right? In other words, it's a direct sum of copies of R. Module. Actually, I want to insert an adjective here. So a free module looks like this, right? And actually, I had written it as R to the m, and you have been thinking of it as kind of column vectors of elements of R. So why do I bother to write it like this instead of just writing R to the m? The reason is that here now we're dealing with graded free modules. Okay? So a graded free module is a direct sum of graded copies of R, but the only subtlety here is that these guys might be graded differently, because we know that we're allowed to shift these guys up and down. So it might be that this guy is shifted by A1, this guy is shifted by A2, this guy is shifted by AM. Okay? So this is like R to the M, but then the top coordinate I choose to shift it by something, the second coordinate I shift it by something else, etc. Okay? So then what's the Hilbert series of F? Well, we said last time that the Hilbert series of a direct sum is just the sum of the Hilbert series. So this is the sum of the Hilbert series of all of these guys. Okay. And now what does each one of these guys look like? Well, we know that if we didn't shift the grading, then this Hilbert series would just be 1 over 1 minus x to the n. And we saw that the effect of shifting the grading by AI is just that you get an x to the AI here. And so what did we get? We got that this is 1 minus x to the n in the denominator, and in the numerator, just get this, which is a nice polynomial. And so that's the end of the proof. Because the Hilbert series of a free module has this form, then the Hilbert series of any module has this form. I think this would be a good time for questions. Any questions? Maybe? Let's see. There's something that I wanted to have prepared on the board when you got here, but I don't know if I should do it, because then I'll take the rest of the hour doing it. Well, maybe I'll give you some definitions, and then maybe we'll do it. But any questions about any of this? Here? No, it's just plus. Yeah. It's just plus because it's just the direct sum of these guys. So remember, here I'm using what I stated, I think, in this corner last time, which is that the Hilbert series of m plus n is the Hilbert series of m plus the Hilbert series of n. That's what I'm using to get this. Oh, I see. Last time, these guys were not. I mean, what's the Betty number here? Well, the Betty number is how many copies of the ring you have, which is m. So if you didn't shift anything, then this would just be ones, and you would get m of them, and that's the Betty number. But if you do shift them, then you're going to get just these terms, one for each one of these guys, and the total number of terms will be the Betty number. Actually, maybe I'd like to state a very general theorem for you right now. Because now we are ready to understand it. I'm trying to do two things at the same time, so don't let me leave this room before telling you what the definition of Kroll dimension is. But I want to address this point, which is an important one also. Let's say that you have a graded module M over R. Okay, so R is this guy, and M is a graded module. Then there is a unique thing called the minimal free resolution, and I mentioned this to you already, but not in full generality. There's a unique minimal free resolution of M. It looks like this. Now, notation might get ugly, but let me try to not let it get too ugly. So there's a unique minimal free resolution of M. So what do I want to say is minimal about this? Well, first of all, what does each one of these guys look like? Let's take some guy R here. Okay, what does this FR look like? Well, this guy is a free module. Okay, but it's a graded free module, which means that it's a sum. It's basically what I just did over here, right? Every free module can be written as a direct sum of shifted copies of R. Okay. And I want to do that, so I need to take a bunch of copies of R and shift them by something. Okay. Now, how many do I have here? Well, this is what I call the Betty number. And I denote it beta R, right? So this should be beta R terms here, and this is the Betty number. Okay. But I also have the freedom to choose these shifts. I need to specify what they are. And I would like to call them A1, A2 up to AM. The problem is that I have to indicate that they depend on R. So the notation necessarily is a little bit uglier. I have to say that this is shifted by AR1 up to ARM. But you see, what's M? M is the number of terms, which is beta R. Okay. So I have to put a beta R here. This is kind of forced upon me, right? I'm trying to be nice to you, but I can't be. And actually, especially for Colombians, this will be very hard to see because they can't see my subscripts. Imagine my subscript of a subscript. AR beta R. So let me say that again. I need to choose these shifts. Over there, I call them A1, A2 up to AM. But over here, I need to indicate that they depend on R because I need to do this for FR minus 1, for F1, for F0. So that's why I have to call them AR1, AR2 up to ARM. But M already has a name. M is the number of terms that I have here, which is the Betty number. So that's why I have to put beta R here. And so I have a big column like this for each one of these guys. And this unique minimal free resolution is going to be minimal in the sense that the length is minimal, the Betty number is minimal, and the shifts are minimal. All of that at the same time. Okay? These are called the shifts. Okay, so this is the Betty number, and these are the shifts, the degree shifts. Each one is a number. So there's a unique minimum Fourier solution of this such that length, Betti numbers, and degree shifts are simultaneously minimized. So this is what I call the unique minimal Fourier solution of M. It's kind of the most economical way to resolve M. And I should also tell you that I could be not just graded but multigraded, right? So if I happen to be multigraded, then the same statement is true. What's the only difference? Well, this is going to look exactly the same. The only thing is that each one of these FRs I have to multigrade. This is not a number, it's a vector. Okay? But everything else is the same. So there is a multigraded version of this guy where these guys are just, the degree shifts are vectors, which is what they are in the multigraded case. Okay. And I think I want to, let me hurry up now because I want to do an example of this so that you see it. So let me just define quickly call dimension for you. Where'd my notebook go? Right here. So you take a graded ring, R, graded ring, write the Hilbert series like this. Okay. We can do this. Where this guy is polynomial. And I want to say something else, which is that this guy has no factors that look like 1 minus x. Okay? Because if I did have a factor of 1 minus x here, I could cancel it and make n smaller. So I want to say that 1 minus x doesn't divide k of this, which is equivalent to saying that k of, when you evaluate it at 1, you don't get 0. In other words, n is the minimal. You basically take the Hilbert series and clear denominator and clear common factors, and it looks like this. This number right here is what we call the call dimension. Okay. Why a dimension? Well, you might be aware that there is a dictionary between algebra and geometry. So given an equation, there is a system of solutions which lives in a geometric space. And basically, if you want to make sense of what dimension means in that geometric space, and this is algebraic geometry, then you have to say what dimension means in this algebraic space of commutative algebra. And it turns out that this is the right dimension, the right definition, and it has nice properties, such as this is also the maximal length of a chain of prime ideals. So if you try to make a chain of prime ideals in your ring, then the longest you're going to be able to make it is n exactly. Okay. And also, when you have a ring, you have a we're talking here about rings over a field, and this is also, and you might have to remind yourself of what this means, the transcendence degree of the ring over your field. In other words, the maximum number of algebraically independent elements. Okay. So this right now is kind of like general culture. These are good things that you should know. I'm not going to prove any of it, but this is another thing that if you're interested in this stuff, and especially if you're interested in going into learning some serious algebraic geometry after this, you could kind of take this and run with it in the project and do something with dimension theory. But this is just a definition that you guys need to have for the homework. So what I want to do, let's see, it's a bit of a challenge to do this in little time, and to make it look decent. But I want to talk about the minimal free resolution for the example that we keep talking about. And I'm going to try to do it very explicitly. So elevator talks today, 4 to 5, don't forget. So you guys know, basically I want to give you the multi-graded version of this resolution. And we last time did the graded version of it, but now I want to do it multi-graded. Okay? So just to remind you, we resolved it like this. And we had some matrices, and I want to do this very carefully. And remember that we had to do some degree shifts, right? So this ended up looking like this, and like this, and like this. Okay, so now I'm gonna do this over here. So first of all, R is just gonna be R. And this is a homogeneous map. We talked about this. Okay? This just takes constants to constants and everything else to 0. Okay, now what about this R? I need 3 copies of R. And here they happen to be graded in the same way, but here I'm going to have to grade them differently. And you'll see why in a second. Okay? So here I actually want to think about it in the way that I drew it over there. I want to think of this as R plus R plus R. And I need to shift these. And here I shifted them all by -1. But here I'm going to have to do something a little bit different. Why is that? Because here the matrix that we multiply by is x, y, z. Right? So that means that basically I'm taking the top component multiplying it by x, the middle component multiplying it by y, the bottom component multiplying it by z, and sending that to here. So for example, the element 1 here gets mapped to x here. Right? So here 1 has degree 0, 0, 0. Here x has degree 1, 0, 0. 1 for x, 0 for y, 0 for z. So that means that I have to fix that grading by shifting by 1, 0, 0. Now, for the middle guy, well, the middle guy actually gets multiplied by this y. Okay? And so that means that I need to shift like this so that, for example, if I take the 1 that lives here, well, 1 looks like it has degree 0, 0, 0, but with this shift, it becomes degree 0, 1, 0. Now, being 1 and being multiplied by that y, it's going to become y over here, which has degree 0, 1, 0. So this is the right grading to make this homogeneous. And by symmetry, you can believe that this is 0, 0, 1. So this R to the 3 actually expands into 3 things that are graded different. What about the next level? Well, I'm going to probably have to do something different as well. Okay. So what was the matrix here? Actually, can you guys tell it to me? Y. Are you going down or? Y minus x 0. Z 0. X 0. Y minus x. 0. 0 z minus y. Okay. Okay. Well, you have to see what these gradings are for this to work out. For example, the identity here gets mapped to y minus x 0. You see, which is the first column. Y minus x 0 doesn't look homogeneous, but it is homogeneous here because y has degree 0, 1, 0, and this bumps it to degree 1, 1, 0. And x has degree 1, 0, 0, and this bumps it to degree 1, 1, 0. So it turns out that the right shift that I need to make is here, -1, 1, 0. And by symmetry, you'll see that what I need to do is -1, 0, 1, and -0, 1, 1. Realize I'm doing this very quickly, but I really want you to stare at this so long that you understand it perfectly. Now here I have a single copy of R. Okay. And if you think about it carefully, you'll see that the right shift that I need to put is -1, 1, 1. And then I get 0. Okay. So stare at this, make sure that you understand why this is homogeneous. But what I'm showing you here is the minimal free resolution of this multigraded module. This is it. Okay. Now I want to kind of publicize something here, so I'm going to ask you to